It's a great pleasure to introduce Maria-Florina Balcan, who goes by Nina Balcan, and she will be talking today about her work in learning theory. Thank you.
Great, thank you very much. So I'll talk about the theory of learning and clustering by similarity functions. But first of all, let me start by mentioning that my research so far has had three major components. The first one has been developing new theoretical frameworks and algorithms for classic and modern learning approaches. The second component has been focused on establishing new connections between machine learning and algorithmic game theory. And finally, I have also been working on pure algorithmic questions, particularly on algorithmic questions motivated by pricing problems. And today, I'll focus on a few pieces of work that fall into the first category. So the outline of my talk is as follows. I'll start by describing some of the most important research areas in machine learning today and my work in these areas. I'll then talk about learning with similarity functions, both in the context of supervised classification and in the context of clustering. And I'll conclude by briefly describing my other work and future research directions. And I'll define what all these terms mean as I go along. And I also want to point out that all the parts of my talk can be followed somewhat independently. So just to start with some background, as a research field, machine learning is concerned with designing programs that adapt from experience. And it is increasingly present in areas of computer science, in applications such as image classification, document categorization, branch prediction, spam detection, and so on. And many of these problems can be modeled by using the supervised learning approach, which is an important paradigm in machine learning. And as a concrete example of a supervised learning problem, imagine that we want to write a computer program to help us decide which email messages are spam and which are important. So what we want to do is to design an algorithm that takes in as input a training set, a set of email messages labeled as spam or not, and produces a good prediction rule for future data, for future messages. And this is called supervised classification, since the learning algorithm uses labeled examples, labeled emails in this case. Now, the first step is to represent each message by a set of features. And for the spam problem, we may design features based on keywords, spelling characteristics, and so on. And this here is an example of a training set. So each row corresponds to a labeled example. It's a labeled email. It's an email message labeled as spam or not. And given this specific data set, some possible reasonable rules that are consistent with the data are predict spam if unknown and money or peers, or if you want to think of yes as being 1 and of no as being 0, then this rule right here would also work. And this is an example of a linear separator in this feature representation, which can geometrically then be represented this way. Now, of course, our goal is to dwell on future data, on new messages, and not only to produce rules that dwell on the training set. And this brings up two important aspects in machine learning. The first aspect is the algorithm design aspect. How can we automatically generate rules like those on the previous slide that dwell on the training set? And the second aspect is what we call confidence bounds or generalization guarantees. What type of confidence do we have that rules that dwell on the training set will also dwell in the future? And for this, there is a very well-developed theory in the context of supervised learning, where under the assumption that the training examples are random samples from the whole population, we can quantify how many labeled examples we need in order to be confident that the rule that does well on the training set on the observed sample will also dwell in the future. Now, concerning the algorithm design problem, what we know to learn best efficiently are linear separators. For many applications, however, very likely the data will not be linearly separable in the most natural feature representation. For example, in the context of image classification, if we want to distinguish images of men from those of women, then very likely the data will not be linearly separable in the most natural pixel representation. All right, so the classic old solution in machine learning would be to try to use or to learn a more complex class of decision rules or a more complex class of functions. For example, in the context of image classification, if we want to distinguish images of men from those of women, then very likely the data will not be linearly separable in the most natural pixel representation. But it may be separable by a more complicated decision surface. And now the classic old advice in machine learning would be to try to learn or to use a more complex class of decision rules or a more complex class of functions. Now this is algorithmically much harder, however, and so the more modern approach, the prominent method in machine learning today, is to something called a kernel. And before going into technical details, let me now mention at a very high level my contributions in the context of kernel methods. As you will see next, as you'll see in a few slides, kernel functions are a special type of pairwise similarity functions, which in combination with a special type of learning algorithms, like SGM or perceptron, allow us to find more complicated decision boundaries, not only linear separators. And again, kernel methods are prominent methods in machine learning today. They are very used in practice, and they do have a solid theoretical foundation. The existing theory, however, is to abstract and disconnect it from practice. Now, in my work, I generalize and simplify the existing theory of learning with kernel functions. So in my work, I develop methods and algorithms that apply more broadly to more general similarity functions that are not necessarily legal kernel functions. And our approach here brings up a new perspective, as well as a much simpler theoretical explanation for the effectiveness of kernel methods, which can then help in the design of good kernel functions for new learning problems. And I'll talk about this in a few slides, but first, let me mention one other increasingly important aspect in machine learning today. And this is, where do we get the data from, and what type of data do we use for learning? So far, I have talked about supervised learning only. For the span problem, for instance, I assume that we have labeled examples only. And this is a classic, the standard learning paradigm. For many modern learning applications, however, unlabeled data is often much cheaper and more plentiful than labeled data. For many modern learning applications, like web page classification, image classification, biology classification problem, we can often generate a lot more data than we can label or annotate manually. And as a consequence, there has recently been substantial interest in the machine learning community in using unlabeled data together with labeled data for learning. And there are currently two main settings which have been considered for incorporating unlabeled data in the learning process. The first one is a so-called semi-supervised learning model, where in addition to a set of labeled examples drawn at random from the whole population, the learning algorithm can also access a usually much larger set of unlabeled examples drawn from the same population. And the goal here is to reduce dependence on the number of labeled examples. For the span problem, for instance, the learning algorithm would also use large amounts of unlabeled emails. Now, a second setting which has been considered for incorporating unlabeled data in the learning process is active learning. And here the learning algorithm is even more powerful, and it can interactively ask for labels of unlabeled examples of its own choice. And so it could potentially learn with even fewer labeled examples by actively directing queries towards informative examples. So active learning and semi-supervised learning are areas of significant importance and significant activity in machine learning. The standard learning theory frameworks, however, do not capture the key issues involved in these new approaches. And while a number of specific algorithms and methods have been developed for these learning techniques, and several successful experimental results have been reported, the theoretical results have been quite scattered, and a solid theoretical understanding has been lacking prior to my work. So in my work, I provide foundational theoretical understanding for these new learning approaches. For example, in the context of semi-supervised learning, I have developed a comprehensive theoretical framework for thinking about the semi-supervised learning problem. And this framework actually appears in a recent book about semi-supervised learning, and it can be used to help explain when and why unlabeled data can help in many of the specific methods in all the other chapters of the book. or in the context of active learning, I have provided both theoretical justification for certain margin-based active learning algorithms, which have proven quite successful in practical applications, as well as designed the first active learning algorithm that works in the presence of arbitrary forms of noise. So, backing up a little bit, active learning and semi-supervised learning incorporating unlabeled data in the learning process is an area of significant importance and activity, and I have worked extensively in this area. And I'm very happy to talk about this after my talk. For the rest of my talk, however, I'll focus on learning with similarity functions. And I'll first start by talking about learning with similarity functions in the context of supervised classification. And in particular, I'll start by talking about kernel methods, which again are prominent methods in supervised classification today. And let me now briefly summarize the existing theory of learning with kernel functions. This will be somewhat technical, and it may be a bit too fast if this is the first time you are seeing kernels. The good news, however, is that one of the main contributions of my work is a new and much simpler explanation of what good kernels are. And so if I go a bit too fast here, just wait a few slides, and then you'll be fine. So formally, a kernel K is a pairwise similarity function that corresponds to a legal definition of a dot product. So specifically, K is a kernel if there exists an implicit mapping phi into a possibly very high-dimensional feature space with a property that K of x, y is a dot product of phi of x and phi of y in that space. So for example, this kernel right here, which is called the polynomial kernel, corresponds to the product into a higher dimensional feature space. This is not obvious, but one can verify it. And now the point is that many learning algorithms, like SVM or perceptron, can be written so that they only interact with the data via dot products. And so that means that if we replace a dot product computation with a kernel computation, then our algorithm acts implicitly as if the data was in the higher dimensional feature space. And it does so without having to pay a high price computationally, without having to go explicitly into the high dimensional feature space. And now hopefully nicer things are going to happen in high dimensional feature spaces, and I'll come back to this. Here is a classic example or picture. The data right here is not on the left, the data right here on the left is not linearly separable in the original two-dimensional representation. However, it is separable by an ellipse, and it is also separable in the phi space induced by the polynomial kernel of degree 2. So, in higher dimensional feature spaces, it's much easier to make the data linearly separable. And moreover, if the data is linearly separable by a large margin in the phi space, then we also get good sample complexity or good generalization guarantees. So for example, if the data is separable by margin gamma in the phi space, then we only need roughly 1 over gamma squared labeled examples in order to learn well. We only need roughly 1 over gamma squared labeled examples to come up with a decision rule, but also on new examples coming from the same source, coming from the same distribution. And this is an example of a generalization guarantee, of a generalization bound that I was mentioning earlier. So, going back to a more generic view, as I've mentioned already, kernel functions have proven very useful in practice for dealing with many different kinds of data. People have written lots of books about kernels, and papers on kernels have occupied a significant percentage at the recent ICML, NIPS, and COLD conferences. These are the most important conferences in machine learning. So for example, statistics from ICML 2007 business meeting show that this was topic number 1 in terms of submissions at ICML last year, and that this is also the topic with the highest increase in popularity in recent years. So, kernel functions are extremely popular. They are very useful in practice for dealing with many different kinds of data, and moreover, there is this nice and elegant theory about what makes a given kernel function a good kernel function for a given learning problem. Now, however, while in practice people think of kernels as just being good measures of similarity, the existing theory talks about margins in implicit high-dimensional feature spaces, which sometimes are even impossible to characterize. And so this is not really great for intuition. It has a something for nothing feel to it. And moreover, the requirement with the similarity function is a legal dot product. The requirement with the similarity function is a legal kernel function, may simply rule out some of the most natural similarity functions for certain learning problems. And so a natural question is, can we develop a simpler, better theoretical explanation? Can we bridge this gap? And the answer is yes. In our work, we provide a theory of learning with a more intuitive and more general theory of learning with more general similarity functions that are not necessarily legal kernel functions. And this theory also formalizes a common intuition that a good kernel function is, in fact, one that acts as a good measure of similarity. And as you'll see, our explanation is very natural. It requires no implicit spaces. It's even more general, and it brings a completely new perspective on learning with kernel functions. So more specifically, in our work, we provide the notion of a good similarity function for a given learning problem, which satisfies the following desirable requirements. First of all, it talks in terms of natural, direct quantities of the data. It does not reference implicit high-dimensional feature spaces, and it has no requirement that the similarity function is a legal, corresponds to a legal dot product. Second, if the similarity function satisfies these properties, then it has good implications for learning. So in other words, if we had the similarity function satisfying our requirements, then we could learn well. And finally, our notion is broad in the sense that it includes the usual notion of a good kernel function. And here by a good kernel function, I mean one that induces a large margin in the implicit high-dimensional feature space. And before going to our main notion, just to get you used to this way of thinking, let me start with a simpler notion. Let me start with a notion of a good similarity function that satisfies the first two requirements. It is extremely intuitive, and it yields an immediate efficient learning algorithm, but which is not broad enough to capture all good kernel functions. And then in a few slides, we'll see how to broaden it. So I'll listen for the classification part of my talk, but we are trying to do binary classification. And that our examples come according to some fixed but unknown distribution P over labeled examples, and that our goal is to achieve low classification error with respect to P. So in other words, you want to come up with a decision rule, but as well new examples coming from this distribution. Now, our first notion says that the similarity function is good for our learning problem if most of the examples are on average more similar to examples of their own label than they are to examples of the opposite label. So formally, the similarity function is epsilon gamma good for our learning problem if at least 1 minus epsilon fraction of the examples x satisfy the requirement that their expected similarity to random examples y of the same label drawn from our distribution is greater by at least a certain gap gamma than their expected similarity to a random example y of the opposite label drawn from our distribution. So for example, assume that the similarity between any two positive examples is at least 0.2, that the similarity between any two negative examples is at least 0.2, but that the similarity between a positive example and a negative example is distributed uniformly in -1, 1. And so that means that the left-hand side here would be at least 0.2, the right-hand side would be 0, and so this would satisfy our definition for epsilon 0 and for gamma 0.2. So this looks like a very simple and intuitive notion of a good similarity function. And moreover, if we have a similarity function satisfying this requirement, then we could learn well by a very simple nearest neighbor style learning algorithm. So specifically, we just have to draw a large enough set of positive examples and a large enough set of negative examples, and then to output the classification rule that classifies a new example x as positive if it's on average more similar to examples in S plus than to examples in S minus, and as negative otherwise. And then the guarantee we get is that as long both sets S plus and S minus have size roughly at least 1 over gamma squared, then with very high probability we get very small error rate. So we can achieve error rate which is arbitrarily close to epsilon, where epsilon is a fraction of the examples not satisfying this inequality right here. And the high-level idea of the argument is as follows. First of all, let's imagine fixing a good example x. So let's imagine fixing an example x that satisfies this inequality right here. Now, if we then imagine sampling the sets S plus and S minus, then we get that the probability of error with respect to this fixed example x is very small. And this follows easily from a standard concentration inequality, like Hovding inequality. Now, since this is true for any given good example x, that means that the expected error rate of our procedure over the set of good examples is small. And so from the Markov inequality, we get that there is a very small chance that the error rate is large. However, it turns out that this is not broad enough to capture all good kernel functions. This notion is not sufficient to capture all good kernel functions. And in fact, we wouldn't even expect this to be broad enough. Since if all good kernel function satisfies this simple condition right here, then we wouldn't need fancy learning algorithms like SVM or perceptron. We could simply run this simple learning algorithm. But to see why this is not broad, let's consider the following simple example. So let's assume that our examples are points in the two-dimensional Euclidean space, and that the similarity function is a standard dot product in this space. Now, if we imagine, let's also assume that the distribution looks like this. So the positive examples are split equally among upper left and upper right, and the negative examples lie all in the lower right. Now, if we choose an appropriate angle right here, in particular, if we choose an angle of 30 degrees, then this similarity function we're going to have, this kernel function we're going to have a large margin. In fact, the margin is a constant, is a half. However, this similarity function fails to satisfy our condition even for epsilon a constant, even for epsilon 1/4. And this is the case since a large fraction of the examples, a large fraction of the positive examples, namely all the positive examples in the upper right, have a higher dot product to a negative example than to a random positive example. So their dot product to a negative example is a half, while the dot product to a random positive example is a half times 1 plus a half times minus a half. Now, notice, however, that if in this simple example right here, we simply ignored all the positive examples in the upper left when computing these expectations over examples y, then we would be fine. And so this suggests modifying the definition as follows. We say that the similarity function is good for our learning problem if there exists a large enough set R of reasonable points such that most of the examples are on average more similar to reasonable examples of their own label than they are to reasonable examples of the opposite label. And note that we do not even need to know the set of reasonable points. We don't even need to know the set R in advance. We only need to hope that the set R exists. And so this is exactly our main broader definition. There exists a set R of reasonable points such that most of the examples X satisfy the requirement that their expected similarity to reasonable points of their own label, drawn from our distribution P, is greater by at least a certain gap gamma than their expected similarity to reasonable points of the opposite label drawn from the distribution P. And we also require that at least that our probability mass of the examples are reasonable positive examples, and that at least that our probability mass of the examples are reasonable negative examples. Now, this is, of course, a broader definition. We have to show that we can still do learning. And it will be more complicated here than in the previous case, but here is the idea. First of all, we can show the following. We can show that if we draw a large enough set of landmarks or a large enough set of unlabeled examples from the underlying distribution, and if we use these landmarks to re-represent new data points, then with very high probability in the new feature space, there will exist a low error large margin separator. So in particular, if we map each new point X into a d-dimensional feature vector, where each entry I is similarity to reference point I, then essentially the same argument that I've done earlier for the simpler definition shows that here in the new feature space, there will exist a low error large margin separator. And so that means that in order to learn well, we first of all have to draw our set of landmarks as we have just discussed. And we would use these landmarks to re-represent new data points. We then take a new fresh set of labeled examples. We map them into the new feature space. And then we run our favorite algorithm for learning a linear separator in this new feature space. And simply output the classification rule produced. Yes?
So these landmarks are just random points?
From the underlying distribution. That's important.
They're from the underlying?
From the underlying distribution, right. And they can even be unlabeled examples. They do not have to be labeled.
They're not necessarily an R, or they
well, they are random points from the underlying distribution. We do not know the set R, but the idea is to have enough representative examples, enough examples from the set R in order to be able to prove it in the new feature space to have a low error large margin separator. And the number of examples, the number of unlabeled examples we have to draw is going to depend on the size of the reasonable set. So in particular, if the reasonable set has a probability mass of at least tau, then we need to draw roughly 1 over tau times 1 over gamma squared labeled landmarks in order to ensure that in the new feature space we have a low error separator.
Question.
Yes?
I'm still not clear what you mean by reasonable. What is a reasonable y?
It's just, yes?
Right, it's a set of reasonable points, but what do you mean by a reasonable point? Right?
It's just a naming. We have discussed this.
No, I said, but like I said, I'm still not clear, right?
Representative points.
Right, but what does representative mean? It just means that they're random samples from the distribution, in which case there's no restriction. Could I just erase the reasonable and everything would still work?
There exists a set of points such that, we can give them any other name, there exists a set of special points such that most of the examples are on average more similar to special points of their own label than to special points of the opposite label.
But you can pick any points that you want for the set R.
As long as, right, definitely, yes, yes.
So why did you ask that they be reasonable?
Oh, it's just a naming. It might not be the best naming. So I'm just saying, so the similarity function is good if there exists a set of special points such that most of the examples are on average more similar to special points of their own label than they are to special points of the opposite label. And we also require that there exists at least a non-negligible probability mass of the points that are special points. So reasonable might not be the best naming, but it's nothing particular about them.
Okay.
Yes?
So you're not finding that special set?
No, but the existence of the special set, let me just go back here. The existence of the special set ensures that in the new feature space we have a good separator. And in particular, there exists a separator that has a very special form. There exists a separator that has 0 weight on the unreasonable or unspecial points and 1 over n plus weight on the, and 1 over n plus on the special positive points and 1 over n minus on the special negative points. So the existence of this set of special or reasonable points ensures that in the new feature space we have a good separator that has low error and large margin. And now we have good algorithms for learning a linear separator, so we just have to apply one of those algorithms. Yes?
I guess there must be some other constraint on the set of reasonable points. For example, it must constitute a significant population of the existing points, because otherwise the reasonable set could be, for example, 1 point for which you could get linear separability, but that wouldn't be enough to, say, learn for the rest of the points. So in other words, there has to be some constraint on that set, other than what's being stated here. Just the existence can't alone guarantee learnability.
It does, because again, so let me just repeat the definition. The definition is that there exists a set of special points, or reasonable points, such that most of the examples X are on average more similar to reasonable points or to special points of their own label than they are to reasonable or special points of the opposite label. And we also have the extra requirement that at least a non-negligible fraction of the points are special points. And now, yes, we do require this, I was mentioning.
That's key.
That was written here. I just, right, so here. I just wanted to remove redundant notation from the slide. Right, of course, the number of examples we need to learn will depend, or the number, in particular, the number of landmarks we need to draw is going to depend on the size of the special set of points. All right? Now, so in addition to So if we have a good similarity function in this sense, then we could learn well by using this learning algorithm. Now, in addition to learnability, we can also show a very nice and desirable property. Namely, we can show that any good kernel function in the traditional sense is also a good similarity function in our sense. And we still lose something in the translation. So in particular, the margin gamma gets squared. But modulo this loss, this provides a formal way to think about good kernel functions as being good similarity functions. And moreover, we can also show that our theory is strictly more general. Namely, we can show that there exists family of learning problems for which a single good similarity function exists, but for which no good kernel function exists. And these are actually the technically most difficult aspects, and I'm going to skip their proofs. I'm happy to talk about them after. And I'll now summarize the first part of my talk. So in this work, we have developed a more general and more intuitive theory of learning with similarity functions that are not necessarily legal kernel functions. So this theory is more intuitive than the standard theory. In particular, it does not reference implicit high-dimensional feature spaces. And it also formalizes a common intuition that a good kernel function is, in fact, one that acts as a good measure of similarity. Yes?
Just to be clear, by good kernel, you mean a kernel that separates the training data with large margin?
Yes, you have not necessarily the training data, the whole distribution.
And as a result?
Yes, the training data in particular, right.
Question?
Yes.
You said in the previous slide that gamma gets squared, but I wasn't clear in your theory relative.
So it can be, so we get a loss in the translation. So in particular, if it's 0 gamma good as a kernel, so if we have a large margin gamma in the phi space, then it can only be gamma squared good as a similarity function. So we do lose something in the translation, in the bounds. But anything that is learnable in the usual sense is also learnable in our sense. We might get an increase in the sample complexity. But however, this is much more general, and it is more intuitive. It does not require talking about implicit high-dimensional feature spaces. Right, and so our theory is probably more general since our algorithms and guarantees apply to more general similarity functions that are not necessarily legal kernel functions. And in fact, let me mention one concrete practical algorithmic implication, which is the following. We can use a similarity function that is not necessarily a legal kernel function inside our algorithm if it's good in our sense. And there is no need to transform it into a distribution-independent way into a legal kernel function in order to plug it into SVM, which would be the more standard, not necessarily well-justified machine learning approach. And in fact, an algorithm similarly to ours has been used by Liao and Noble here at the University of Washington in the context of protein classification, and they did obtain state-of-the-art results for their problem, and our theory justifies their approach. And let me now show how we can use this perspective in order to actually help think about the clustering problem in a novel way. And first, let me start by mentioning that although the study of clustering is centered around an intuitively very compelling goal, and although clustering has been used in many sciences for many years, it has been very difficult to reason about clustering at a deep technical level from a learning perspective, in part due to the lack of general unified frameworks along the lines we have for supervised classification. And in the remaining time, I will describe how our work on learning with similarity functions for supervised classification inspired the similar framework for clustering. And since, in fact, one of the main contributions here is a precise framework in which you can quantify success and failure of clustering algorithms, I will start with a precise definition of the model. So let's assume that we have a set S of an object, say n documents, and let's assume that there exists some unknown ground truth clustering, some desired clustering. That means each object has some label, say its topic, and that our goal is to produce a good clustering or a clustering that has low error up to isomorphism in the names of the labels. And so now that this goal is very similar to the standard classification goal, it is slightly weaker since we do not care about getting the names of the clusters right. We only care about getting the clusters right. However, the problem is that we have unlabeled data only. But luckily, is usually in a clustering setting, we have a similarity function. But hopefully, it is somehow related to what we are trying to do. Hopefully, our similarity function is related to the topicness. And so given this context, the fundamental question that we address in our work is what natural conditions, what natural properties in the similarity function are sufficient to allow us to cluster well. And again, just to recap, just to be precise, the precise protocol here is the following. We assume that there exists some correct desired clustering for our set of objects. That means each object has some labels, say its topic. However, we do not get to see the labels. We only get unlabeled data and the similarity function. And the goal is to produce a clustering that is close to the desired correct ground truth clustering. And so clearly, given this goal, given this context, the similarity function has to somehow be related to the correct ground truth clustering. Otherwise, there is no hope, since we have no labeled examples. And so given the context, the fundamental question that we address in this work is what natural properties or natural conditions on the similarity function are sufficient to allow us to cluster well. And before presenting some of the main results here, let me describe how this framework relates to other clustering frameworks. First of all, the common practice to clustering in the algorithms community is to assume that we have as an input a graph or an embedding of the points, say in RD, and then the goal is to analyze abilities of various algorithms or approximation algorithms to achieve various optimization criteria, like k-means, k-median, mean sum, and so on. And so in this classic algorithm view, the algorithms, the clustering algorithms are scored based on which of them produces a better ratio, a better approximation ratio for the given objective at hand. And also occasionally, people argue about which of the objectives produces a better looking result. Now, in our work, we flip the perspective around a little bit, and we view the clustering problem as effectively one of learning from unlabeled data by a similarity function. And so that means that in our work, we score the algorithms based on the error rate, and this is more natural since in many learning-motivated applications, like clustering documents by topic or web search results by category, the input graph, the input similarity, and so the input graph are merely based on some heuristics. And what we really care about is recovering the correct desired ground truth clustering rather than optimizing some specific graph property. So this is more natural. And in fact, in this respect, we are closer to work done in the area of learning or clustering with mixture models. There is one big difference. There is one difference, however, we do not have strong generative assumptions about the underlying distribution. We do not assume mixture of Gaussians or log concave distributions, for instance. So we are analyzing a more flexible, in learning theoretic terms, discriminative framework for clustering, not a generative one. And again, given our setup, the fundamental question that we address is what natural conditions or natural properties in the similarity function are sufficient to allow us to cluster well. And as you expect, and as you'll see, we're going to need more restrictive properties on the similarity function here than in the classification setting, since we have no labeled examples at all. And let me now start with a condition that just completely, totally trivially works, and then we'll see how to weaken it. So if we had the similarity function such that the similarity between any two examples, say the similarity between any two documents is positive if they are about the same topic, if they are in the same cluster, and negative otherwise, then clustering would be completely trivial. We wouldn't even need a clustering algorithm in this setting. So let's just weaken this condition slightly to say that all the points X, all the documents satisfy are actually more similar to points or to documents in their own cluster than they are to points or documents in any other cluster. So this is still a very strong, quite strong condition, and yet it's not enough to cluster well. The main problem being that the same similarity function might satisfy this very simple looking condition for two very different clusterings and perhaps arguably equally natural clusterings of the same data. So for instance, in this example right here, if the similarity within each of the four blobs is 1, the similarity top down is 1/2, and the similarity across is 0, then both the clustering on the left and the clustering on the right we're going to satisfy this condition with respect to our similarity function. And clearly, there is no way to tell which of them is a ground truth since we have no labeled examples. And moreover, unlike in a classification setting, we cannot even test our hypothesis, again, since we have no labeled examples. Now, in our work, we overcome this problem by considering two relaxations of the clustering objective, which are very natural in many applications. And the first relaxation we consider is what we call hierarchical clustering. And here we allow the clustering algorithm to output a hierarchy or a tree on subsets such that the correct ground of clustering is the pruning of the hierarchy. So for instance, a natural hierarchical decomposition for the document clustering example on the previous slide is this one right here, or maybe this one. And so in this setting, we do not require the clustering algorithm to output the single correct ground of clustering, but we allow this type of hierarchical output, and we then ensure that the correct ground of clustering is the pruning of the hierarchy. And this desired clustering can then be identified with a little bit of additional feedback. And this effectively corresponds to clustering algorithm saying, I wasn't sure how specific the user wanted to be, but if any of these clusters is too broad, just click on them and I'll split them for you. And again, this is very natural since the clustering algorithm might not know in advance how specific the user wanted to be. He might not know if the user wanted 2 clusters for fashion and 1 for sports, or actually if he wanted the other way around, 2 clusters for sports and 1 for fashion. Now, one other relaxation of the clustering objective we consider in our work is list clustering. And here we allow the clustering algorithm to output a list, a small list of clusterings, such that the correct desired clustering is close enough to one of the clusterings in the list. And this is similar in spirit of list decoding encoding theory, and we can, of course, imagine trading off the strength on our assumption with the size of the list produced. Good. Now, with this relaxation of the clustering objective, we now obtain a rich model in which we can analyze both sample complexity, clustering complexity, and algorithmic results. And we'll still need some more restrictive properties here than in the classification setting since we have no labeled examples, but it turns out that a number of interesting learning theoretic and game theoretic properties can be defined which allow an algorithm to cluster well. And let me now give a few concrete examples of results in this framework. First of all, if the similarity function satisfies the simple strict separation property I was mentioning earlier, then we can probably output a hierarchy. And we can argue that in this case, a simple single linkage bottom-up algorithm works. So the algorithm here is very simple. We just start with all the points in their own parts, and then at each moment in time, we just merge the 2 parts whose max similarity is the highest. And then what we can prove is that if the similarity function satisfies this strict separation condition, then we can use the single linkage algorithm to output a hierarchy or a tree on subsets such that the correct desired ground of clustering is the pruning of the hierarchy. Now, a broader and more interesting property that we have analyzed and which is still sufficient for hierarchical clustering is the stability property, which actually is the analog of stable marriage property in the context of clustering. So specifically, I'm going to say that the similarity function satisfies the stability property if for any 2 clusters, say for any 2 topics, C and C prime, for any 2 subsets, A subset of cluster C and A prime subset of cluster C prime, neither A or A prime is more attracted to the other one than to the rest of its own cluster. Now, it turns out that this is again sufficient for hierarchical clustering, and we can argue this by showing that, again, a simple average single linkage algorithm works. And we can, of course, imagine analyzing more relaxed properties than the simple strict separation property and the stability property. And in particular, an interesting one which looks a lot like some of the properties in the first part of the talk is the average attraction property. So most of the points satisfy the property that where expected similarity, where average similarity to points in their own cluster is greater by at least a certain gap gamma than their average similarity to points in any other cluster. Now, it turns out that this is not sufficient for hierarchical clustering. However, we can still guarantee a small list output, and we can find the list by using a standard property testing algorithm. And right, and we have also analyzed a number of other properties, and in particular, an interesting one, an interesting intermediate one is the stability of large subsets property. So we require that the stability property that I was mentioning earlier holds, but only as long as the sum of the sizes of the two subsets is large enough. Now, this will of course cause simple linkage bottom-up algorithms to fail. However, we can still guarantee the existence of a hierarchy, and we can find the hierarchy by using a more sophisticated multi-stage learning-based algorithm. And let me quickly mention the main idea, the main steps involved in this algorithm and in the proof. First of all, we're going to use the average attraction algorithm to generate a list of candidate clusters with the guarantee that any cluster in the ground truth is close to one of the clusters in the list. Then we run a second tester algorithm. Namely, we're going to run a second tester algorithm and we're going to throw out some of the clusters in the list. So specifically, for any pair of clusters C and C0, which are sufficiently non-laminar with respect to each other, we're going to run a pairwise test. And we're going to throw out some of the two clusters, one of the two clusters. And then the claim is that by appropriately setting the parameters, we can guarantee that we're never going to throw out the representatives of the correct clusters from this list. And then finally, we just have to do a little bit of cleaning and hook up the surviving clusters into a tree. So this is the main idea of the algorithm and also of the proof. And let me now summarize the clustering part. So in this work, we have developed a new general framework for clustering. And within this framework, we have been exploring minimal conditions on the similarity function that allow it to be useful for clustering in the sense of producing an accurate solution. And in order to get useful, interesting results, we have considered two relaxations of the clustering objective, hierarchical clustering and least clustering. And in both of these cases, we allow the desired correct ground of clustering to be identified with a little bit of additional feedback. And our notion of a property parallels the notion of a data-dependent concept class. It parallels the notion of a large margin separator, for instance. And more generally, this framework parallels Park's statistical learning theory framework, learning with kernels and similarity functions in the context of supervised classification. And now in terms of technically most difficult aspects, which I didn't talk about, let me mention some of them. So first of all, some technically interesting aspects of the following: designing algorithms for the case on most of the points, but not all the points satisfy the simple stick separation property. Also designing algorithms for stability of large subsets property, as well as designing algorithms and conducting analysis for the inductive setting, which is a setting where the set of points S is just a random subset from a much larger abstract instance space, and the goal is to produce a clustering that is good for the whole instance space. For instance, here, in order to adapt our algorithm in order to adapt the stability property to the inductive setting, we have to consider a version of the definition with a gamma gap, and we also have to show that sampling preserves stability. And for this, we have used a regularity-based argument. So now the overall summary. So in this work, we have been analyzing what type of similarity information is sufficient in order to produce an accurate solution, both in the context of supervised classification and in the context of clustering. And in the context of supervised classification, we have generalized and simplified the existing theory of learning with kernel methods, while in the context of clustering, we have provided the first clustering framework for analyzing accuracy under no strong probabilistic assumptions. Finally, in the last few slides, let me also briefly mention some of my other work in algorithmic game theory and machine learning. So first of all, my work in algorithmic game theory includes both an exciting applications of machine learning techniques to automate aspects of mechanism design and also formally address the issue of market analysis, as well as pricing algorithms with improved guarantees over previous methods. So for example, in the context of auction design, I have provided a generic framework for reducing more difficult problems of incentive-compatible auction design to standard algorithmic questions for a wide, and I did this for a wide variety of revenue maximization pricing problems. And I have also developed approximation and online algorithms again, for pricing problems, and again in the context of revenue maximization, both in combinatorial auctions with single-minded customers and in combinatorial auctions with general valuation functions. And in the context of machine learning, in addition to the topics I've talked about today, learning with similarity functions, I've also worked on a number of other topics. In particular, I have explored connections between kernels, random projections, and feature selection, as well as various ways of incorporating unlabeled data in the learning process. And I have briefly talked about this at the beginning of my talk. Now, in terms of future directions, I definitely plan to explore new connections between computer science and economics. And I'm particularly interested in using machine learning techniques to automate aspects of mechanism design and to analyze the overall behavior of complex settings, of complex systems, where selfish agents might use their own learning algorithms. And now, in terms of machine learning, I am very interested in studying interactive learning. And in terms of specific questions related to what I've talked about today, let me mention a few of them that I plan to explore. First of all, I'm very interested in developing theory-end algorithms for learning a good similarity function based on data from related problems. And this both in the context of supervised classification and in the context of clustering. And in the context of clustering, one interesting direction to explore is analyzing other navigational structures. For instance, a DAG, a small DAG, instead of a tree, when the similarity information is not enough to produce a tree. And I'm also generally interested in analyzing new properties on the similarity function motivated by real-world applications arising, for instance, in vision or biology, as well as extending the clustering framework to accommodate limited but interactive types of feedback. And also more broadly, I'm interested in designing better interactive learning algorithms. And also, even more broadly, I'm interested in using machine learning techniques in other areas of computer science and in other sciences. Yes.
So your clustering framework seems to exclude many simple cases that can easily be handled by the graph-based approaches. Like, for example, when you have two spirals winding around each other.
No, it doesn't exclude. So so in this work, we've analyzed a number of properties in the similarity function and what type of algorithm is appropriate given a certain property. Now, for instance, the case you are mentioning, so we could imagine coming up with a transductive similarity function. And in your case, I think we could define a similarity function given the set of unlabeled points, and we could perhaps...
Okay, so but what do you mean by transductive similarity function? Doesn't that require an extension of the framework that you were talking about?
So...
That's exactly the problem, is that there's a transductive aspect to that, right? How do you, I don't see where you take that into account.
So for instance, you could define, so you can start with a base similarity, which is maybe the distance, Euclidean distance, and then you can come up with the graph based, and we're going to have a certain graph for the specific setting we are mentioning, and then we can define a new similarity function that says the similarity between the 2 points is high if there is a short path in between the two in this graph. And then I think that it's actually very likely that that similarity function is going to satisfy even the simplest separation property.
Okay, so, but in essence, you'd have to do the graph-based approach first, right? What you're saying is assume like somebody's going to create this graph, and then on top, if you have a similarity measure defined on this graph, right, then
we can use one of these clustering algorithms. But the main point here is that we are trying to understand what condition the similarity function motivates using what type of clustering algorithms, and moreover, given a certain clustering algorithm, what is a condition of the similarity function that allows us to cluster well. So I wouldn't say that my framework excludes the simple example you're mentioning. And we have analyzed a number of properties. There are probably many other natural ones that one could imagine. And this is something that I plan to explore. So it's similar in supervised classification. If we believe that the target function is a linear separator, then we're going to run a linear separator learning algorithm. Or if we believe that it's a decision tree, then we're going to run a decision tree learning algorithm. So here, similarly, we want to understand, given a certain property, what type of clustering algorithm do you want to run. So it really parallels that framework. Yes, please.
So since this is kind of like a supervised clustering setting, the interesting thing about it is that labels seem to be more expensive in a supervised clustering setting than in a supervised classification setting. Like, why do you go after a clustering approach? It's probably because you don't have access to lots of labels. And so, you have to be very efficient at getting the ground truth in the clustering.
And one of the points that we are making is that if we really want to get the ground truth, then you really need a very strong condition on the similarity function. But if we actually relax the clustering objective, for instance, if we allow ourselves to output a hierarchy, then we can get many more interesting results. So this is one of the main points of this work.
Okay, let's thank the speaker again.